Hello physics students, this is Dr. Brenzi. This is lesson 2.1.3. This is the second video in this lesson. In the first video we talked about solving second law of motion problems, Newton's second law, and using that with a force or free body diagram to figure out, like, say, what the force is in a particular cable, or what the acceleration is in a certain direction. We're going to expand that now in this video to problems in 2 dimensions. Now, the process is the same as dealing with problems in 1 dimension, except after you write your second law equation down, you're going to actually break it into its x and y components. So just like what we did in the last unit with projectile motion, when you have projectile motion in 2 dimensions, we wrote an x and y and we separated those. Well, you're going to do the same thing for force or free body diagrams in the x direction and in the y direction. So you're actually going to have an F net equals MA for forces that are horizontal, and you're going to have a separate F net equals MA for forces in the vertical direction. So that's the only difference between 2 dimensions and 1 dimension. So let's go ahead and try to apply this to a problem. Now, if you were in class today, you already got this problem, but it's good to review this, and it's also good to have this in case we need to study for a formative, or if you just want to review this concept, or if you were gone from class today. So I have an interesting diagram here where I have 2 ropes. I have a rope A and a rope B. Let's make that text bigger. A rope A and a rope B, and they are both suspending a 15 kilogram mass. And this 15 kilogram mass we are going to assume is at rest. So, first thing I have to do is the same thing I had to do in 1 dimension, and that is to draw a free body diagram. So this is my 15 kilogram mass. We have the force of gravity acting in this direction, F sub g, and we know that that equals mass times the acceleration due to gravity, and that equals 15 times negative 9.8. Okay, so I know the force due to gravity. I have a tension in this direction. No, going to the left. We are going to call that F sub t comma A. So the tension force due to rope A. And we also have a force going in this direction, and that is the force of the tension in rope B, or the tension force in rope B. Okay. Now this lies all along vertical direction right here. This lies all on horizontal direction. But this one has components both in the vertical and the horizontal direction. So what I want to do is I actually want to break this thing up into its components in the x direction and the y direction. So let me first move that label. I should have put it over here. And what I'm going to do is break this up into its components. So let's draw a right triangle. So we're going to have a horizontal vector going this way and a vertical vector going up. And the 2 of those added together will give me this vector right here, the tension force due to rope B. Okay, well, how do I figure out what the force, or the component in the x direction is and the component in the y direction is? Well, we have to bring in our friend Sohcahtoa. We have a right triangle. There's our right angle. We know that this angle is 50 degrees. Okay. So if I want this angle down here, what does that have to be? Well, that also has to be 50 degrees because we have two parallel lines. This is parallel to that. And these are what are called alternate interior angles. So alternate interior angles are congruent when two parallel lines are cut by a transversal. So this will also be 50 degrees. So I can go ahead and say that this is 50 degrees right here, this angle, 50 degrees. Okay. Now I'm ready to use some Sohcahtoa. Sohcahtoa. All right, so let's see. If I want to figure out, I know what the hypotenuse is. Right? This is the hypotenuse. I know what that is. If I want to figure out the opposite, then which of these trig functions do I need to use? Well, sine is equal to opposite over hypotenuse. That involves what I do know. That involves what I want to know. So the opposite is going to equal f sub t comma b times the sine of 50 degrees. This one, the adjacent side, is going to equal the tension force in B times cosine of 50 degrees. All right? Okay. So I'm going to now split my screen in two, and I'm going to have x direction over here. I'm going to have y direction over here. And my x direction, we have this force. Well, actually, I forgot one thing. I'm skipping ahead. I better make sure I write F net equals MA. And I also have to write F net equals MA for both of those. So now let's go ahead and work with the x direction here. So let's write down what our net force is. Our net force is equal to the tension in rope A plus this force right here. The force due to tension in rope B times cosine of 50 degrees. And that equals my mass, 15 kilograms, times acceleration. Now, this problem isn't telling me that this is accelerating up, down, left, or right, so my acceleration is 0. Okay, because we can assume it's staying at rest. Well, 15 times 0 is just 0, so we can just put a little arrow there and say that equals 0. Well, that doesn't look too helpful right now, because we're trying to figure out what this is and we're trying to figure out what that is, but we don't know what either of those is yet, so it looks like we're at a dead end, but we haven't figured out anything over here yet. So let's hold off giving up until we actually work through our y direction. Okay, so now in the y direction, I have to write down all my forces. So in the y direction, I have the force due to gravity. And now I've already figured out, well, actually, let's just write that down first. We'll plug in numbers in a little bit. And then I also, in the y direction, have the y component of this force. So I also need to include the force of tension in rope B times sine of 50 degrees. And that equals mass times acceleration. Okay, let's start plugging in some numbers here. So the force due to gravity, we've already figured that out. That's 15 times negative 9.8. Let's go ahead and plug that in. We don't know the force and tension B, or force due to tension in rope B yet, so let's keep that the way it is. F of T comma B times sine of 50 degrees equals mass times acceleration. Oops, it's 15, not 16 kilograms. Times acceleration. What is the acceleration? Well, I know that the acceleration in the x direction is 0. And if this ball is at rest, the acceleration in the y direction, it also has to be 0. Its velocity is not changing in any direction whatsoever. So I'm going to put 15 times 0. Well, that's equal to 0. Okay, well, this is looking like a lot of work, but I'm not going to give up on it just yet, because what I noticed as I looked through this entire equation here is that I'm just left with one unknown, and that is this number, right, or this variable right here, the force, the tension force in rope B. So I can actually go ahead and solve this for the tension force in rope B. And when you do that, if I remember right, I get something like the force and tension B. Oh, God, I keep on saying that. The force of tension in rope B, it turns out to be something around 191 newtons. Okay? So that is the tension of rope B is 191 newtons, and that's going in this direction. All right, so that answers part of our question, but we also have to figure out the tension in rope A. Well, how do I figure this out? Because I still have two variables, but I now know the value of this variable. I get that over here, so I can plug this into here. There it is. And then solve for the force due to tension in rope A. So after you figured out what the force of tension in rope B is, you're gonna have an equation that looks like this. You're gonna have, oh, that's a bad color to use there. Let's try a different one. How about purple? The force due to tension in rope A plus 191 times cosine of 50 degrees equals 0. Now that's definitely an equation we can solve, right? Right. So when you solve this and get the force of tension due to rope A by itself, it turns out that happens to be somewhere, if I remember right, in the neighborhood of 120 something newtons. So I'm just going to put 120 newtons, approximately. And since it's approximate, I'll erase that and put my approximate symbol. All right. Okay, so that is how you find the tension in rope A and in rope B. This took a lot of work, didn't it? And we even had, for a little while, a system of equations that we had to solve. But thankfully, one of those equations, this one over here, only ended up with one variable in it so that we could solve, and then we had to use substitution to plug it in over here, and then find the force of tension in rope A. Now that was a lot of work, and I do understand that that was a lot of work. But we are also in advanced physics or in AP physics, and sometimes you have to buckle down and do a lot of hard work. But you're all smart people and you're all capable of doing it. You just need to practice and persevering in solving problems like this and not giving up on them too soon. All right, I'm going to show you now an even tougher example. So if you thought that one was tough, we're in for a real ride here. So buckle your seat belts. We're in for a crazy one here. All right. Now I know my video is getting long here, so I'm not going to get into this too much. Well, I am, but I'm going to try to skip little things along the way that I think that you can solve on your own. All right, so the first thing we want to do is we want to draw a force body diagram on this 119 kilogram ball here. So I have a gravitational force working in the downward direction, which is equal to m times g, little g. And let's go ahead and figure out what that is. That turns out to be 119 times negative 9.8. And if I crank that in my calculator, that turns out to be negative 1,166 newtons. Okay. I also have, I'm going to bring this up a little bit here, just so it meets these two ropes right there. So we have a tension force in this direction. We're going to call this rope B. And we're going to call this one, I better give it a different color, rope A. Well, actually, I didn't need to give it a different color. So let's go back to red. Rope A. Okay. All right, so there's my free body diagram. And the next thing I need to do is I want to get this all into horizontal and vertical components. So I have some work to do. I better make a couple of triangles right here. So let's make one. Let's make one of them orange. Whoops. Let's make one of them orange. And let's make one of them blue. Let's make the other one blue. Here we go. Blue. All right. Well, maybe not quite. All right. So I have two triangles now. All right, so now I can split the tension in rope A into two components. Let's see, instead of, actually better call those by their forces, so instead of just calling A and B. So this is the force of tension in rope A. This is the force of tension in rope B. Okay, so the same names that we had last time. Okay, now I'm going to trust that you know how to break these into components. We know this angle. If I look at this triangle over here, we know that this angle is 20.3 degrees. Why? Because that's 20.3, and we have alternate interior angles again. So let's mark that as 20.3. I know that that's quite a little bit of space there. All right, so this is going to be f of t comma a times sine of 20.3. This is going to be f of t comma a cosine of 20.3. Boy, that's really small writing there. There we go. Okay. I was wondering if there's a way I could zoom in, but. Okay, this is the force due to tension in B times, since this is adjacent, or no, excuse me, opposite, this would be sine of 79 degrees. And this one down here, let's not put the arrow there. Let's put it, all right, let's put it right here. The force due to tension in rope B times cosine of 79 degrees. Right. Now I can split it into x and y directions. X, y. All right, so let's write Newton's second law. F net equals ma. F net equals ma. And let's go with the x direction here first. So in the x direction, I have this force right here, and I have that force right there. I don't have any other forces in the x direction, so let's see, f of t comma a. So I'm writing this force down first, times cosine of 20.3 degrees plus this force right here, the force due to tension in rope B, times cosine of 79 degrees, and that equals mass times acceleration, but my ball is not accelerating in the horizontal direction, so I can just set this entire thing, m times a, equal to 0, because there's no acceleration in the x direction. The ball's not changing its velocity in the x direction. All right, so starting to look like a pretty intimidating equation. It looks like we have two different forces. All right, so there's nothing I can solve for just quite yet. But let's not give up because we still have a y direction. So let's go over here and add up all our y forces to find F net in the y direction. We have, first of all, the force due to gravity, and we already found out that that's negative 1,166. Right. We have this force, this component of the tension, so that's the force due to tension in rope A times sine of 20.3. And then we have to add this component because it also is going in the y direction. So the force of tension in rope B times sine of 79 degrees. All right, so all of that added together, this plus that, give us our F net. What are we going to set F net equal to? Well, mass times acceleration. Acceleration in the y direction. Does it have acceleration in the y direction? No, it is at rest. So we can set m times a. For this particular problem, we can set that equal to 0. And that also means that this equals 0. Okay, so it looks like this even looks hairier than this one over here, doesn't it? So I still have those same two variables. I have two equations for two unknowns, and I have a system of equations to solve. Wow. Okay, now before I go into this system of equations, let's do a little simplifying here first. Let's evaluate what these trig functions are. And when you evaluate them, or when I evaluate them, cosine of 20.3 is equal to something around 0.938, and cosine of 79 is something around 0.191. So let's go ahead and plug those in. So f of t comma a times, this one is 0.938, plus f of t comma b times 0.191. All of that equals 0. All right. Here we have negative 1166, plus, I need to now figure out what sine of 20.3 is. Sine 20.3 equals 0.347. Now over here I put my coefficients afterward, but I could have just as well put them before. And I think I'm going to do that practice over here. And let's see, now I also have to figure out what sine of 79 degrees is. Sine 79, boop, equals 0.982. Wait a minute. Okay, yeah, never mind. Okay, I thought I saw that number before. 0.982 f of t in row B. All of that equals 0. Okay. So now I have two equations, two unknowns. All right, now let's pull up a blank slate here. And let's try to remember how to solve systems of equations. All right, so, if I could only rewrite this on a new slide. Hold on here. Oh, no, didn't want to do that. Did want to do this. Oh, no, I didn't want to do that. All right. No. All right, now I've done myself in. Oh, jeez. Oh, this is so embarrassing. All right, so. No, don't want to do that. Okay. Whiteboard. All right. So, how do we solve that hairy system of equations here? Now, I'm not going to actually finish solving that until I give you a little intro. Well, no, that's not. No, I'm just going to go ahead and solve it. All right, so what did I have here? All right, so I had, if I remember right, the force of tension in rope A. Let's put the coefficient first this time. 0.938 force of tension in A plus 0.191 times the force of tension in rope B equals 0. And the other one I had, I'm going to start off with the force of tension in rope A. And we're going to say that is 0.347 plus 0.982 times the force of tension in B, minus 1,166 equals 0. Okay? Now, I can solve this in one of two ways. So systems of equations can be solved either by elimination or they can be solved by substitution. All right. I think I am going to show you how to solve this one with elimination. All right, so what I want to do is I want to take one of these equations, probably this one, because oops, excuse me, this one, because this one is, this one doesn't involve a constant. So I'm going to take this one, and what I want to do is I want to find a factor that will change this into the opposite of that. You're saying, what? What do you mean? Wait a minute, Dr. Brenzy. So what I'm going to do is I'm going to take this equation, I'm going to pull it down here. So let's take this one, and we're going to multiply everything times this fraction right here. Negative 0.982 divided by 0.191. And you might be saying, Dr. Brenzy, what is going on here? Why are you trying to do this? Well, if you hang in there with me for just a moment, you're going to understand why I chose this particular fraction to multiply into my equation, this top equation right here. So let's rewrite that top equation. 0.938 force of T in rope A plus 0.9191 times force in T, comma B, right? And if I multiply this side times this fraction, I also have to multiply the other side of this times that same fraction. So to be fair, I would end up with 0.982 negative divided by 0.191 times 0. Okay? Well, what's that entire thing going to be on the right-hand side? It's a number times 0, and any number times 0 just gives me 0 in return. 0. Okay. So let's go ahead and use the distributive property to multiply this times that, and then multiply this times that. All right. Now actually, let's do this one first. Let's do it in the regular order. All right, so if I multiply this fraction times this coefficient, I get something 0.982 negative. Oops, except I need my calculator to react to me. Come on, calculator. All right, negative 0.982 divided by 0.191. And we're going to multiply that times 0.938. And I get negative 4.82 times the force of tension in rope A. Now, let's do the same thing. Let's finish our distributive property to distribute this fraction into that. But let's be a little bit smart about this, because what I'm going to end up with is I'm going to end up multiplying something with this number in the denominator times something with that same number in the numerator. So these will end up actually dividing out, and what I'll be left with is just this number right here. So I'm going to end up with negative 0.982 times the force due to tension in rope B. All right, and you're saying, Dr. Brenzy, so what? Well, now you're going to see the magic. You're going to see why I chose to take this number, which is the same as this one, the opposite of this one, put it on top, and why I took this number and put it on bottom. Here comes the magic. Okay, I'm going to rewrite this equation, this one right here. I'm going to rewrite it below. Okay, and along with that, I'm also going to move this 1166 over to this side by adding 1166 to both sides. So you're actually going to see this one over on this side. Okay, so let's go ahead and move that equation down here with that little change. So 0.347 times the force of tension in rope A plus 0.982 times the force of tension in rope B equals 1,166. Because again, I just added 1166 to both sides so that I could get it over there. I could have done that earlier, but, well, hindsight is 20/20. And this has already been a long video, and I don't want to tape it again. All right, we're almost there. Now here's the big magic. When I add this equation to this equation, watch what happens. So I'm going to add like terms. So I'm going to add this term to that term. And negative 4.82 plus 0.347 equals negative 4.473. And I have the force of tension in rope A plus what? Well, I have negative something plus positive of that same thing. When you add those up, they equal what? 0. 0 equals 0 plus 1,166 equals 1,166. We have eliminated this term f of t for rope B. We no longer have that in our equation. We're just left with one variable now. We're just left with this times that equals this thing over here. You can solve that, right? You can solve that for the force of due to tension in rope A. Okay, so we found the force of tension in rope A. What do we have to do to find the force of tension in rope B? Well, you need to take this number that you got, you need to plug it into either of these equations, but if you're a wise person, you're going to choose this one because it's shorter, and you're going to then have an equation that only has FTB in it. And then you're going to be able to solve for that, and you're going to be able to find the force of tension in rope A and the force of tension in rope B. And there your problem is solved. Woo-hoo. Yes, and my voice is totally hoarse. I can't even woo. So that was a long problem, wasn't it? But you are AP kids. You're college bound. You're probably going to go into engineering or physics. And if you're not, you're also, you're smart anyway. You can handle a tough problem like this. It just requires some grit, requires some patience, and you can do it. And this is why you've been taught in Algebra 2 how to do systems of equations by elimination and substitution. There you go. A real-world application of solving systems of equations is finding tension in a rope. I don't know if you'll ever tie 2 ropes to a ball, but now you know how to figure out the tension in them. So, all right, it's been a long video, both for me and I imagine for you, but it is a long process. We're going to have an opportunity to practice this process in class tomorrow, and I hope you have an awesome evening. Bye.